And so we're going to talk about the vectors and matrices today. Time. All right, so what is vector? So there are many ways of defining vector, but let me start from the most primitive way of defining it. Vector, so for here, I'm going to give a different name. It's a position vector. We call it PQ and put an arrow on top. Is of a vector from two-dimensional point P. Let's say P has a coordinate x1, y1, and Q as coordinate x2 and y2. So this is the information that we need to define a position vector, and position vector is a tuple of real number. The tuple of real number defined the following way. So it has also two coordinates, but it's a vector. So in order to distinguish from the tuple of the points, tuple of numbers that represent a point, I'm going to use the bracket here, not the parentheses. And the entry are the subtraction of each entries of the coordinate of the point. So you need 2 points to define a position vector, and usually we say the arrow is the object that represents the vector. So P is called the start point. And Q is the end point. So this is easy way to define a vector, but you will see that it's a little bit unnatural in some sense, but let's take this as a definition. So whenever you have mathematical objects, try to think about this as a something that you can visualize or computable. So let's visualize our vector with Python. So collab. Oh. Sorry. One quote. Okay. Okay, so we're going to use the matplotlib again in this case. So let's say import matplotlib pyplot. And when you draw, so I want to draw the arrow. So the arrow can be drawn with a function called quiver. And this takes at least 4 inputs. The first input is the coordinate of the point P, the start point, and the second input is coordinate of the endpoints Q, and let's draw it here. So when you simply draw this quiver, I think it's a little bit time to load the figure. The figure is not really good. You can see that it's not scaled well. It's kind of direction is correct probably, but scale is not right because it starts from 0, 0, but the length is too short. It only goes up to 0.01. So you need some option here. So the best way of doing the option is the following way. Let's see. It's all in the book, but so here let's see, angles is following the XY option, and scale units is also XY, and scale is also 1. Let's do it again. So now you can see that the arrow is actually the same size as we intended here, but the screen size is not properly contains the entire arrow because it only goes to up to 0.5, 0.5. So let's see. I want to make x-axis to minus 2 to 2, and y-axis. Sorry, that's not the axis. So it's y limit and x limit. And y limit from minus 2 to 2. So now you can see the arrow here. So the window is from minus 2 to 2 on x-axis and y-axis from minus 2 to 2. And then the arrow starts from the 0, 0 and goes to 1, 2. You can see the arrow here. You can draw many arrows too. So if you want to draw another arrow, you can just put another quiver function here. Let's say I want to make a quiver from 0, 0 and minus 1 and 1. So remember that this 4 inputs are, sorry, so I made it wrong. So it's the second input is not the coordinate of the endpoints. It's the coordinate of the vector. So I'm putting this vector. So for example, if I change the starting point, let's say 1, 1 here. Let's see what happens. Oh, I need the same option here. So you can see that the first arrow starts from the origin. The second arrow is starting from the 1, 1, and it's not pointing to minus 1, 1 point. So minus 1, 1 point is here. It's not going this way. So it's actually going to the left by 1 and then go up by 1. So this minus 1 and 1 comes from the coordinate of the vector, this PQ vector. So the Q is actually adding 1 to minus 1 and 1 to 1. So the Q is actually 0, 2. So you're not putting the endpoints, coordinate of endpoint, you're putting the coordinate of the vector for the second two inputs here. Okay, so that's the important part you have to remember when you draw the quiver. All right, so any questions about this? I want to make it completely elementary here because back in old days, people, I mean, Korean students at least, learned about the vectors in high school. You do? Did you learn vectors in high school? Raise your hand if you learned vector in high school. I mean, so I think Raise your hand if you didn't learn vectors in high school. You didn't? Raise your hand if you didn't learn vector. Everyone learned about the vectors. Okay, so, but I just want to make completely elementary here. So the vector is something you can do some kind of a vector operation. So let me introduce two vector operations here. So the first vector operation is the vector addition here. Vector operation. So the first one is vector addition. If you have two vectors, let's say OP plus PQ, I think we all know about this, but this will be quite weird if I say a different way. But anyway, we can find another vector where it matches to, it eliminates the midpoint here. So basically, if I have an arrow from 0 to P and P to Q, it can combine into 0 to Q, just taking the first, the starting point of the first vector and the end point of the second vector. And you can do the same way with several vectors. And the second one is that you can take scalar multiplication. So if I have k as a real number, then this PQ is the scalar multiple of k times PQ is the scalar multiple of the vector PQ. So what does that mean? So if I had PQ equals to, let's say, x1, y1, or just xy, sorry, then it's a vector k times n, x, and k times y. K times x and k times y. Do you see something is weird here? Yeah, something weird. So what is, so if I have k times pq, so then how do I write it in terms of this notation? What is these two points? What if I have to write, this is a new vector because it's a tuple. I wrote that the sum of two vectors is OQ here, but I didn't write this as some kind of a OQ or something similar. Well, what is it here? What it has to go here? What does have to be here? So, so here, let me introduce another terminology. So here, definition, two vectors. So it's position vector. Two position vectors. Let's say PQ and P prime Q prime is called parallel. If they have the same coordinates. So if I have a point P and point Q here, and my vector has arrow represented as an arrow like this, and if I have the same exact arrow and then translate to another place, and now the starting point is P prime and the end point is Q prime, then they are called, so these two vectors are called parallel. But how did I define the position vector? Position vector is just the tuple of two numbers, right? So if they have the same coordinate, they are the same tuple. So if they are actually the same tuple, they are the same thing. no matter where the starting point is, if they are the same, if two vectors have the same coordinate, they are exactly the same object, right? So two parallel vectors are actually the same vectors. So here remark is that two parallel position vectors are the same vector. Okay, so you have to understand this meaning, same vector. They're the same thing. So vector is not really an arrow, because if you want to draw an arrow, you need a start point. But vector can be represented as an arrow, but it is not arrow. Okay? So therefore, it only depends on where the arrow is pointing, right? And then not just the direction, it also matters with the size. So when I say vector, then it only means that this direction and size of the arrow, not where the arrow is starting from. So whenever they have the same size and direction, we call it the same vector. The reason why I say position vector is because whenever we need to represent the vector as an arrow, we need a starting point. Inevitably, we need a starting point. That's why we just put the different name in position vector. But usually, we don't say position vector. We only say it's a vector. All right, so, and also position vector is sometimes very useful when we talk about the geometric object like lines. So think about the lines here. How do we represent a line? How do we figure out the coordinate on a line, of a point on a line? So think about this way. So remark, a line is determined by either, so first is if you have two distinct points, let's say P and Q on the line, or if you have a point on the line and a parallel vector which is parallel to the line, right? So one point P and a vector V, you can call it a position vector if you want, but let's call it V, parallel to the line. So if I have one first condition, if I have this way, so the line is here and I have point P here and Q here. If I want any point inside of this line, then I need to know how far should I move along this line from the point P, right? So I just need this vector, this arrow. So let's say this is Px, the arrow is Px, and this only indicates the direction and size from P and X. But when you want to determine the absolute coordinate, absolute position of this vector, you need an origin. You need the base point. So let's say we have an origin here. So then your coordinate of the point X, coordinate of X, let's say if I have write the coordinate of X as X comma Y, then the coordinate of OX, the position vector, is also X comma Y. So now how do you write the OX here? So OX is OP plus PX, right? By the definition of the vector addition. And how do you get the PX? So that's where you have a scalar multiplication. So PX and PQ are having the same direction, but differing only in the size. So that's what the scalar multiplication means. So if you take the PQ vector, and let's put an arrow here. So PQ vector is this arrow. If you want to change the size but keep the same direction, then you can multiply some constant. Probably if you want to make it shorter, then you need the number less than 1. If you want to make it longer, you want to multiply number bigger than 1. So then you can make px. So this px can be written as some constant k times pq. So if you find the coordinate of OX, you can find the coordinate of a point on the line. And this OX is determined by OP, which is already given because we have the PQ information. And also the vector PQ. And also it's known because we have a PQ coordinates. So this K is the only thing that we can change to change the point on the line. So this X, coordinate of X, only depends on K. So for example, if I have this way, so if I have PQ, P as A1, B1, and Q as A2 and B2, what is OX here? So this is A2 minus B2, A1 minus A2 minus A1, B2 minus B1 plus K times, this is A1, B1. So A1, B1 plus K, A2 minus A1, B2 minus B1. So this is my X and Y. So if you want to write the coordinate of the point on the line passing through the PQ, then X is A1 plus K, A2 minus A1, and B1 plus K, B2 minus B1. So it's a parametric equation basically. So you can, if you want to follow the curve, then you can parameterize your X coordinate of the point with the parameter K and Y coordinate as also the same parameter K. So let's draw this. So if you want to draw the graph, you use the vector. So here, so let's say we have P and Q. So I'm going to introduce another way of writing, defining a vector using NumPy. So NumPy, import NumPy. And let's see. So the P is 1, 1, and Q is, let's see, 1, 1, maybe 2, 1, something like this. And so my X, let's say K, the parameter, is running from minus, say, 2 to 2. And where do I have? So X, the coordinate of my point X, X coordinate of my point X, it's called the small x here, is given by what? Q, let's say P, so P0 plus K times P1 minus P0. First I'm doing it inconvenient way, and then I'll show you how to do it on the convenient way. So sorry, not P, Q here, Q0. And Y coordinate is P1 plus K times Q1 minus P1. Right? So P0, P1 is the X and Y coordinate of P, and Q0, Q1 is the X and Y coordinate of P, Q. So now let's draw the point. So plot X, Y. Let's see what happens here. PQ, Q1, Y, PQ. Oh, sorry, 2, 1. Yes. So it's not interesting. So it's a flat line. So let's make it 1, 1, 2, 2, 3, I think. Yes, make it this way. So you can see that, so where is the P point? So P is 1, 1. So right here, P is 1, 1 here. And Q is 2, 3. So 2, 3 is somewhere here. So P, Q are 2 points on the line right here. Let me indicate those 2 points. So by dot. So here we have 1, 1. So let me write it this way. P0 and P1 with dot here, and we can have the same thing with the Q here. It's a bit small, so let me change the size, marker size as 5. Maybe 10. Okay. So this is P and this is Q. And I draw the points on the line with changing my K from -2 to 2. So when K is 0, I'm at P. You see, when K is 0, I'm just having OP and nothing more, right? So I'm at the point P. So when K is 1, I'm moving from OP and at PQ, so I get OQ. So I'm moving up to point Q. So that's when I have K equals to 1. So and then if I have K equals to 2, what happens? I move another PQ direction here, so I get to this far. So what about when K is negative? So you can see there is a negative part, exactly same length as this part. So when I have K negative, I'm moving in opposite direction. So opposite means that it's the opposite of this direction. So I'm moving in this direction. So it's go far that way. So when you draw the line, you can only draw the finite line. Of course, cannot draw the infinite line, but mathematically you can find K equals to any number, so you can get an infinite line. So ideally, that's the way you can use our vector addition and scalar multiplication in mathematical settings to define a line. So you remember when I said about the calculus in the beginning of the class? The calculus is about differentiation and integration. The differentiation is about making everything into a line. So that's why it's the understanding line and how to represent the line is very important. This notation, this idea will be appeared many places in our material. Oh, by the way, so this is about the two-dimensional point, two-dimensional vector. How do we draw a three-dimensional vector? Let's draw one. So if you want to draw a three-dimensional picture, you need a special environment. So in the figure, and add subplot, and you need an option called projection equals to 3D. So an axis also has the same function called quiver, and let's draw 1, 1, 1. So this is the same thing. We need a 3 coordinate of the three-dimensional point, which is the starting point of an arrow, and the next 3 entry input is the x and y and z coordinate of the three-dimensional vector. And then let's put option here. So arrow length ratio equals to 0.1. And okay, so and also I need to set the x limit to be -1 to 1. And same for y limit and z limit. Now you can see the three-dimensional arrow here. So let me make it smaller. So everything is same, except that we have a 3-dimension instead of 2-dimension. If you want to get the 3-dimensional line, what do? You just draw 3-dimensional points and connect it with a line. So for example, let's do it this way. So I have a starting point P as a three-dimensional point. Let's say it's 1, 1, 1. And the vector parallel to the line that I'm going to draw is going to be 1, 2, 3. And let's take the parameter numpy array from numpy in space from -1 to 1. Let's draw the line. So basically, line is just a graph of a linear function, and we're gonna talk about this next chapter 3 or 4 when you draw the graph. But here, let's use the environment, three-dimensional environment here. Let me make it bigger. So when you draw the point and also point connected with line, use the plot, the same function in the three-dimensional environment. And what I do is I'm going to use this way. So P plus K times PQ. And I'm going to use change the axis here. So let's change it to -5 to 5. So I really have to explain before I move on, but let me check whether it works first. Yes, I think it doesn't work it this way. So yeah, I think I'll do it next time. So let's see. So P0 is the x coordinate of the starting point, and add with PQ, and y is P1 plus K times PQ, and z is P2. That's the z coordinate of PQ, and x is plot xy and z. So PQ, oh, sorry, so PQ0, PQ1, PQ2. Okay. Now we can see the line here. So if I have to draw the P and Q point here, so let's draw it again. So X is plot P as a dot. So bigger dot here. If I put the O instead of dot, it means bigger dot. And I also want to plot the Q point. So my PQ is 1, 2, 3. What is Q then? So I have to translate this PQ vector so that the starting point becomes origin, not the P. So I have to subtract this coordinate 1, 2, 3 by 1, 1, 1. So the Q coordinates is going to be PQ minus P. Minus P. Okay, so let me draw here and then, oh, what happens here? PQ, let's see. Wait, P, why is this point not on the line here? PQ, K times PQ, 1, 1, 1, 1, 2, 3. PQ 0, 1, 2, and PQ. PQ. So let me just draw the coordinates here. So it's 0, 1, 2. Right? I think there's something wrong going on. So we have P 0, 1, 2, 3. I want to move to 1, 2, 3, right? Oh, sorry. So I made a mistake. So we have a P from P on here, and plus PQ here. I have to add, not subtract. Sorry. So my point Q is P plus PQ, not PQ minus P. So P plus PQ. Yes. So then I have a point here. Okay. So it actually goes through this wall, but I didn't make the x and y axis big enough to have an entire line here. So anyway, you can see the line and the 2 points on that line in 3 dimensions. The same works. So let me show the code here so you can see the code. All right. So, okay, so far so good. So let's talk about the vectors itself. So now we have a position vector. This is for visualizing the vectors with an arrow, and it's useful when you visualize anything. But in fact, we need to understand the nature of vector. So what is vector? So here's definition. So actually, the vector is comes with the dimension. So two-dimensional vector is a tuple of real numbers. And if you have three-dimensional vector, that means it's a triple of real number that satisfies following. So first, if you have tuple of two numbers here, and you can add them together. When you add them together, you have to add coordinate-wise. So x1 plus x2 and y1 plus y2. And that's called the vector addition. And the second operation is whenever you have vector and a scalar, just the real number, then you get another tuple with multiplying this k on every coordinates, kx and ky. So whenever so this is actually an object, a tuple, and this is called the two-dimensional vector. If you want the three-dimensional vector, what you do? You replace these by triple of numbers. So here x1, y1, and z1 plus x2, y2, z2 equals to x1, x2, and so on. The same thing here. So k times x, y, z is kx, ky, kz. So this is two-dimensional vector and three-dimensional vector. So I'll introduce lots of terminology, and then if you want to see an example, I mean, if it's clear, then you can move on. If you want to see an example, and the definition is not clear to you, let me know and let me stop and then give you an example. So let V1 to Vn be the same, let's say not n here. Let's say k be n-dimensional vectors. Then the linear combination of them is a vector of the following form. So you have C1, which is constant, multiplied on the first vector. So it's a scalar multiplication just defined in here. And you add C2, V2, and up to CK, VK. So everything is a vector. And every time you add another vector, you get a vector. And then add another vector to get a vector. So it's a vector. But this vector can be represented as this form. So you get another vector by adding and multiplying scalar from the given k vectors here. So it's called a linear combination. It appears many places in mathematics, also in lots of subject that involves mathematics. So you have to understand what the linear combination means. Basically, if you can find any expression similar to this, you can call it linear combination. So here's another definition. So we define the vector, but there is something called vector space, and it is the set. So vector space also comes with the dimension. So n-dimensional vector space is a set of all n-dimensional vectors. Okay. So, and also we denote R2 to be the set of all two-dimensional vectors. So in other words, this is x comma y, where x and y are all the real numbers. And R3 is the three-dimensional vectors. So you can easily generalize to n-dimensional vector, but we're not going to talk about four-dimensional or five-dimensional vector because we cannot visualize. And it doesn't mean that it's not important, but simply understanding two and three-dimensional case is enough to understand general case. So we're gonna just focus on these two. And so here, another definition here. The inner product of two n-dimensional vector. So whenever I say n-dimensional, imagine n is either 2 or 3, okay? V, which is x1, y1, and it's v1, and v2, where it's x2, y2, is a real number defined by, first denoted by v1 dot v2. So it's just a notation, and it represents a real number computed by x1, x2 plus y1, y2. Okay. So in this case, it's two-dimensional and if it's three-dimensional, let's say x1 to z1, and here x2 to z2, then the inner product is x1, x2, y1, y2, and z1, z2. Okay. I don't want to write again, so just understand what it means when it's two-dimensional and three-dimensional. So actually, when you try to understand the vectors, you have to understand the inner product. What does inner product do? So here's the important theorem. First, let me start from this case, this definition. So the norm, the size, or called norm of vector V is the number, real number, denoted by double bar around V, and this is square root of V inner product V itself. So we call it norm, the size. So let me introduce a theorem here. And also, and before I theorem, sorry for keeping you up here. So let's say V is called a unit vector if its size V is 1. So if you compute the size of vector and it turns out to be 1, then it's called the unit. So it's just a length of 1. So here's the theorem. So let V and W be, for example, two-dimensional unit vectors. And let's say this is a position vector here. So position vector. And let's say we have v equals to 0p and w equals to OQ here. Okay, so in the picture we have O, which is the origin, and P is here and Q is here, and we can draw the two arrows here. And let's say this theta is the angle in between two arrows. Okay, and theta is the angle between arrows of OP and OQ vector. Then the following holds. So if I take the inner product between V and W, it's cosine theta. I'm going to prove it because I think it's very important to understand it. And then think about after proving this theorem and what's the meaning of the inner product. So first, we assume that it's a unit position vector. And our starting point is the same, the origin. So the P and Q has the same coordinate as the vector V and W. So P, Q are lying on the unit circle, right? So P, Q are points on the unit circle, the circle of radius 1 with the center at the origin. So the coordinate of the point on the unit circle is the cosine and sine. So let's say P is the cosine theta 1, sine theta 2, and Q is cosine theta 2 and sine theta 2, theta 1 here, theta 1 here, 2 here. So if I draw this way, so this is my P point, and this is my theta 1, and let's say this is Q, and this is my theta 2. Okay. So these are the coordinates of vector V and vector W. So let's try to compute V inner product W. So how this is defined? So first you take the two x coordinates and multiply them together. So it's a cosine theta 1, cosine theta 2, and then you add multiple of two y coordinates plus sine theta 1 and sine theta 2. Do you know anything, do you remember anything about the sine addition formula here, or cosine addition formula? This is cosine theta 1 minus theta 2, right? And you can also write as cosine theta 2 minus theta 1 if you want, because cosine is an even function, doesn't matter. So what is theta 2 minus theta 1? This angle, and it's theta. It's the definition of theta in our theorem. So this is cosine theta. So what do we showed here? The vector two vectors V and W are inner product to get cosine theta. So what does it mean? What does it mean? So it's not that we have an angle because, so it's not that we need to know the theta in order to get the inner product. It's the theta we get after taking the inner product, because inner product is already given from the coordinate of the vectors. We can get the inner product without knowing the angles of these two vectors, right? So inner product defines the angle in some sense. So what does angle means? When you have an angle, what do you get? So I'm going to just make a layout of the concepts here. So inner product gives angle. So why do you care about the angle in many cases? What does angle give? If you want to throw something into some angle, you want to control the direction, right? So angle gives the direction. And what does inner product also gives? So just before we define what the unit vector is, inner product defines the size of the arrow, size of the vector, norm of the vectors. So it also defines the size. So whenever you say vector, we often say it's an object with the size and direction, right? So where does this direction and size come from? It's come from the inner product. Okay. So inner product is the important concept. Without inner product, there's no direction, there's no size. Okay, so here's an example here. Let's talk about some example. All right. Let's say I have a vector of coordinate 1 over square root of 5 and 2 over square root of 5, and v2 as coordinate 1, 0. And suppose that I know that w is unit vector, and v inner product with w is 3 over square root of 10, and v1 here, v2 inner product w is 1 over square root of 2. Find the direction of w. What do you mean by direction? I want the angle. I want the angle of w. So I already gave the size. So size is 1. It's normalized. So I don't care about the size. It's given. I only want which direction is this vector is pointing at. So whenever we talk about the general vectors, you can consider it as an arrow pointing from the origin. So the first vector is somehow 1, 2 direction. So it's something like here, v1. And v2 is pointing in 1, 0 direction. So it's actually parallel to x-axis. So these are two, v1 and v2. And I don't know whether, I mean, for now, I just don't have any information about the angle of W. All I have is these two information. I'll give you some time to find out the coordinate of W and then find out the direction of W. Try to find out the W. You can either find the coordinate of W directly by this equation and try to get the angle, or you can use the formula that if you take the inner product between two unit vectors, you can get the angle between these two vectors. So I'll give it some time to answer this question, find the direction of W. Okay, so I think most of you guys are confused where to start because if I asked find out the coordinate of W, you probably have started working on. But because I asked find the direction of W, probably you guys are confused what to do. What kind of answer are we expected to see? But that's exactly the point because, well, this kind of question will be the question that you will see on the midterm or final. I'm not going to ask a specific value or something that you can get from the formula, but I'm going to ask you to formulate your question in your own language and then try to answer with the explanation here. So what do you mean by finding the direction? You have to explain the direction. How do you explain the direction? Yeah, find the angle, but angle without any standard basis or standard axis have no meaning. Like I have a space here, I have an angle of 5. What does that mean? So it has always be the relative angle, right? From this axis, I have an angle of degree of something. From this axis, I have degree of something, right? Then you can find out what direction you're talking about, right? So the direction itself is not a number or something that you can like, this is the direction. You have to explain the direction, right? So we have two vectors, definite vector, absolute vectors. I already draw two vectors as an arrow. If I want to explain the direction according to these two vectors, I have to explain what angle does this vector W is at according to these two vectors. So let's look at the first one. So it says the inner product is 3 over square root of 10. So by the theorem, since these two are unit vectors, if theta 1 is the angle between V1 and W, what can I say? 3 over 10 square root of 10 is cosine theta 1. Okay? So what theta 1 satisfies this equality here? We don't know, but it doesn't mean that it doesn't exist because it's not one of the value we remember as a cosine value. So we have to compute with a Python here or calculator if you want to. So there is a function called arc cosine, which is inverse cosine, arc cosine, and 3 over square root of 10. And there are square root function in the NumPy package also, which is sqrt. So and then let's see, something 0.32, and it's in radian. So let's see, the T1, and I'm going to convert it into degree. So T1 times 180 minus divide by pi. So pi is stored as a constant in NumPy package. So it says it's 18.43 degree. Okay. So this much. And we kind of know, I mean, we have an idea of how much this angle is. We're used to make an angle of 360 degree. So the angle that W make with the V1 is 18.4 degrees. So it might something like this or this. So actually there are two, right? So this or this. Which one? I only used one piece of information. To find out which one is correct direction, I need to use the second piece of information. So let's say I have theta 2, which is the angle between W and V2. And in that case, 1 over square root of 2 equals 2 cosine theta 2. And I know what that is because it's the well-known value of cosine. It's 45 degrees. Which one you think is 45 degree? This one or this one? The second one, right? It seems like it's the second one. So, yeah, I can draw it, but how can you explain the direction then? So the direction of W is the angle between W and V1 is 18.4, and the angle between W and V2 is 45. That's the answer. But can you change it? Can I change the statement a little bit differently? Of course. If you say the same thing, I mean, you can say different way, totally different way, but the direction you're talking about is the same direction. Comparing your explanation, that's the answer. So you see what I mean by when I ask a question, I'm not asking what is the inner product of these two vectors. Compute. Well, I'm not interested in computing that, because computer can do that for you. I want you to be able to explain the concept, explain what you mean, explain what the terminology is. And sometimes it might not be clear when I say direction, but then you have to interpret that terminology in your own language, in your own understanding, and then explain it as much as you can do. Okay? That's the idea. All right, so let me give another example. Since we know the type of question that I like, so how about this one? So we have so we have a vector whose size is square root of 5, and I have the inner product with V1 is 5, and inner product with V2 is 6, and find the direction of W. Oh, by the way, I didn't give you the what. Wait. Forgot to note. I forgot to take a note on the coordinate V1 and V2. I think that's actually the example in the textbook. So let me find the coordinate of V1 and V2 here. Which one was it? Not this one. It's, so yeah. So V1 is 112, and V2 is 013. So actually, it's a three-dimensional vector. A more accurate way of putting this question is find the directions of vector W. So also, because V1, V2 are three-dimensional vectors, by definition, you also have the W as three-dimensional vector. Otherwise, the inner product doesn't make sense. So I want you to think about these questions. I mean, of course, if you can find the answer and try to compute. But first, think about the questions, what you're going to do, what you have to do. What would you want to do? What would you want to do to find the direction of W? You first want to make a drawing, probably, right? If you want to know, if you want to have an idea what the direction of a vector is, the best way is to draw an arrow, right? Arrow that represents three-dimensional vectors. How do you draw the arrow? You need a coordinate, right? You can set the starting point as an origin, and the end point will be the point whose coordinates are the same as the coordinates of the vector. So you need the three coordinates of this vector W. That's one way. That's the one way you can get the idea of concept of the vector direction. Or you can start from the angle the angle information, right? But then you have a problem. Okay, I introduced the angle between two vectors when it's unit vector, then the inner product is the cosine theta. But it says that it's not a unit vector. The norm is not 1. And also, the theorem that I mentioned is about two-dimensional vector. So you can ask whether the same thing happens for three-dimensional vectors. Does inner product between two three-dimensional vector equals the cosine of the angle between the arrows? So there, you can see the expansion of thinking going on here. You have to think yourself what I should try to do in order to get close to the answer. Sometimes the question, if you go further, you find out the question itself doesn't make sense, and then you have to make it clear which point the question is not making sense. So let's do it this way. So first, I want to find coordinate of W. Okay, let's say I put the W coordinate as A, B, C, or can I X, Y, Z here? Whatever variable you want, just put it that way. And then let's convert all the information I have here. So the first information says that I have A squared plus B squared plus C squared, which is the inner product of W by itself, right? Equals to what? Square root of 5 or 5? 5, yes, because I didn't take the square here. The inner product, the norm is the inner square root of inner product. And how about this one, the second one? We have 1 times A, 1 times B, plus 2 times C equals to 5, right? And how about the other? 0 times A, 1 times B, plus 3 times C equals to 6. Okay, can I solve a unique solution? It's not the same system of linear equation. It's not linear here, it's just quadratic. But still, I can try. That's the first way to find ABC using these three sets of formula here. And I can just find the angle, theta 1 and theta 2. And there are many problems here. So if I have a two-dimensional vector on a plane, the angle, the meaning of angle is apparently clear, right? But what do I mean by angle between three-dimensional vectors? So it's a three-dimensional picture here, it's three-dimensional space. I have vector here, I have vector here. Let's say V1 and W here. What do I mean by angle here? What do you mean by angle between these two three-dimensional vectors? You have to figure out that one first. So let me write the question. What do we mean by the angle between two vectors, two three-dimensional vectors? Then another question, if suppose that you solve this, you clarify the meaning of the angle. And how do we get the angle? That's another question. But you can guess how to get an angle because we have a formula that V1 W equals to cosine theta, but that only applies to unit vectors and two-dimensional vector, and you want to generalize to non-unit vectors and a three-dimensional vector case. So you can have a hint from this formula. And then, well, the last one, if you say you've figured out what this angle means and how to get an angle, and last question might be how to express or explain the direction using two angles. Because it was relatively easier in two-dimensional case, because if you have two angles on the plane, then you can draw it somehow. But in three-dimensional, how do you explain the angle in three-dimensional space with two angles? That's another issue here. So where do you want to start? Which path you want to go? Yep. All right, let's work on the equation here. How do you find ABC? Yes, you can find, but here, this one is not linear. So, but the linear function, linear equation, there are only two linear equations, so you cannot find a unique solution. But you can try to represent one variable in terms of other two, or two variables in terms of another variable. For example, so this one gives A equals to 5 minus B minus 2C. And let's see. Okay, so yeah, sorry. Yeah, so let's start from here. So it's simpler here. So B equals to 6 minus 3C. Okay, so let's say B is now a function of C. So now I can replace B here. So it's 5 minus 6 minus 3C minus 2C. So it's 1 plus C, right? So A is 1 plus C and B is 6 minus 3C. So you can plug that in here. So replacing A and B. So you get quadratic equation in terms of C, right? So then you can find the root. So usually if you have a root of quadratic equation, you have two. You have two roots, right? So you get the two candidate of number C, but for each case, you get a fixed A and B. So you can expect to get two candidate of the coordinates of the vector W satisfying these informations, right? Okay, so once you have that, you can draw. So even drawing could be an explanation. I'm not saying you have to explain always by words. So once you have two coordinates, two sets of coordinates of the vector, then you can draw them and you can claim that, oh, the direction of the vector is what this arrow is pointing at. But that's perfectly nice explanation about the direction. Yes, so that's one way you can get. Okay, so how about second part? Well, let's first think about the first question. What do you mean by angle of two three-dimensional vectors? How do you define an angle between two three-dimensional vectors? Imagine two sticks on your in front of your eyes. So there is a stick, and this stick, say, represents the arrow of three-dimensional vector. These two sticks, like let's say I used arms here, so get here. Then, how do you measure angle? Divide by what? Inner product with the size. Well, so angle is geometric object. So we're gonna talk about the arithmetic formula to find the angle. And I want to talk about how to define the angle. Angle is a geometric object. How do you understand angle as a geometric object? Yeah, I'm talking about the angle between two vectors. Okay, so let's not think about the conditions here. I just want to think about the angles, because I want to explain the direction in terms of angle. Imagine the line is on the same plane. Line is on the same. Two lines are on the same plane. What do you mean by two lines here? What are these lines? In terms of these vectors. So if I have vector, yeah. Say it again. Yeah, so W and V1. Line is the W and V1. W and V1 is the vector. Line is just infinite line. Yeah, the parallel vectors, right? So imagine that you have a line. We can have an arrow too. Imagine that you have two lines, each line parallel with the vectors, each vectors, okay? And these two lines are lying on the same plane in 3 dimensions, right? You can find a unique plane containing two lines intersecting at one point. So imagine the vector as an arrow, and these two arrows has the same starting point, let's say origin, and you can extend this arrow to make a line, right? So since these two lines are intersecting at one point, there are unique plane containing these two lines, right? That's intuitively clear. And what do you do next? I mean, the finding part is the second part. How do you define the angle? Well, that's how you compute the angle. This is the angle, right? Yes, yeah, defining angle. So, yeah, it's maybe intuitively so clear. If it's too clear, then it's hard to explain in words, but it's still important to put it in words. So angle between two three-dimensional vector is the angle on the plane in three-dimensional space which contains two lines or arrows which intersect at one point, and the angle is the angle between these two lines measured at the intersection. Okay. So of course you can say, oh, which direction are we measuring the angle? Because you can measure angle in this direction or that direction. It depends on the starting point, and it changes the sign. When it changes the sign, the cosine theta and sine theta changes the sign too. But however, when you take the cosine theta, the measuring direction doesn't matter, right? Because cosine is an even function. So now it naturally leads to the question, second question. How do we get the zeta, the angle between these two vectors? So here's the theorem. So let V and W be n-dimensional vector, not only just two-dimensional vectors, it's n-dimensional vectors. And the angle between V and W is zeta. So now you know what we mean by the assumption here. Because if the assumption is not clear, then the theorem doesn't make sense. You have to clearly understand what I mean by angle between two vectors. Okay? Then V inner product with W is, so I didn't assume that V and W are unit vectors. So here is the norm of V, and here's the norm of W, and then multiply with cosine theta. That's the inner product. Again, this is not the definition of inner product. Definition of inner product is given by the sum of multiple of coordinates of two vectors. So this is something we can compute without knowing anything about the angle, right? And you can also get the angle geometrically just drawing your vectors as an arrow. And this is what you can get. And you can also get the size of the two vectors either by taking the inner product by itself or simply drawing the arrow here. And that's why it's a theorem. The left-hand side and right-hand side can be computed independently, right? And then it's still the same, okay? So you can use this right-hand side as a formula of computing the inner product, but that's not the definition. It's a theorem, right? All right, so if I have this, then what do you get? Cosine theta is same as V inner product W, V times W size. If you really want to get the theta only, then you can get the theta as the inverse of cosine function divided by V and W. Okay. So by the way, when you take the inverse cosine, it doesn't give you the answer between 0 and 2 pi. What's the typical range of inverse of cosine? The range of inverse of cosine. What's the codomain of the inverse of cosine function? Negative pi to pi. So here we have cosine function. Let's draw the graph of cosine function. Yeah, the good guess, but let's draw it that way. But let me extend a bit here. So in order to get the inverse function, you need to have one-to-one correspondence. So this is clearly not one-to-one correspondence if you take the entire real line as a domain. So you have to take a subinterval. Usually we take this much. Then it's one-to-one. So it's one-to-one from 0 to pi, and the codomain of cosine here is 1 to minus 1, right? But when you take the inverse, you flip the graph. So the inverse function now takes 0 to pi as a codomain. That's the range of inverse of cosine. And minus 1 to 1 as an input. So the graph of inverse of cosine looks like here, like this. So this is, let's say, y, and this is theta. So it's a cosine value here, but it's a input of the arc cosine inverse. So it's 1 and minus 1. So arc cosine takes the value in between minus 1 and 1 and gives the value between 0 to pi. Okay. So you can imagine your theta will always be, if you compute this way, 0 to pi. So let's compute our angle here using this information. So and numpy cosine of, what was it? Forgot. Let me get this. Right, so first, the first angle, T1, is the angle between W and V1. So the inner product between two vectors is 5, and I divide it by the size of vector W, which is square root of 5, and then divide out by the size of V1. I know that V1 has a coordinate 1, 1, 2, so it's a square root of 6. So that's T1, so angle in radian. So I want to print out in terms of degree. So it's basically 24.1 degree. And let's compute the second angle here. So inner product is 6, and same norm for W, but the norm of V2 is it's 0, 1, 3, 10. So square root of 10. And T2, T2. So the first angle, T1, is 24.1, and second angle is 31.9. Okay, I have two angles. Now, how do I explain that? So let's go back. Let's go to the third question. So now I know the angle. I compute the angle. I know what that means is, what that angle means. So the third question, how do I express the direction using these two angles? If you put it naively, you can say it this way. So W is pointing at direction where it makes an angle of 24.1 degree with the V1 vector and 31.9 degree with the vector V2. Well, that's not false statement. That is what direction means, but it doesn't really, give any intuition about what really the direction is about. So I think someone actually mentioned about the cone. Who was it? Was it you? Did you mention about the cone before? Yeah, cone. Yeah. So can you explain again what you mean by that? Uh-huh. Yes. 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 Cone satisfying the given conditions. Yes. Do you want to explain more, or shall I elaborate your explanation? Okay, so let me just elaborate a little bit more on what you said here. So, okay, so instead of just plainly explain the meaning of the theta 1 and theta 2, let's try this way. I have, where's my, so I have two angles, and let's say this is my V1. So I don't care actually this is the correct direction or not. I just say this is my V1 direction. And all the vectors have the angle between V1 with 24.1 degree make up a cone, make up a surface of a cone. So here, This is my cone. So where does 24.1 degree come from? So if I have an axis of the cone and take a one rim of the boundary here, then this is 24.1 degree. Okay. So if I have this information, then my vector W will be pointing somewhere on the surface boundary here. So the vector W will be here, could be here, 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 on the surface of the cone. Of course, it has the size of square root of 5, so that's why he mentioned, what's your name? What's your name? Yes. So Hongyu mentioned about the sphere of radius square root of 5, because I only want to talk about, so this is the origin, the vector that is up to the boundary of the sphere of radius square root of 5. But anyway, since we were talking about the direction only, we can forget about the sphere right now. Now, that's not the only information. We have another angle. It says 31.9, and let's say this is my V2. And if I have 32 degrees, let's say this is my angle. This is my cone, whose angle is 31.9 degree. And if I only have this information, my W could pointing the direction on the surface of this cone, right? But I have two information, and W has to satisfy these two pieces of information at the same time. So then what can I say? The only direction that W can have is intersection of these two cones, right? That's more intuitively clear, right? It's clear that it has two directions. That cannot be clear if I just plainly say that W has an angle between V1, V2 with these angles. It doesn't carry out any knowledge about how many directions are there. But if you explain with the cone, the geometric object, then it's intuitive. Of course, it doesn't have to be always two directions. It could be one direction if the cone are tangent each other, or it could be, it could be not intersecting at all, right? But in this case, you can also draw the cones, two cones together, and then see where that intersects, and then pointing out that these two directions are the direction of the vector, possible directions of vector W. And also by just plainly situation about these cones, people can understand what you mean by that. And also it's sometimes useful than having a coordinate of W, having this kind of information. Right? So I'm trying to explain many things here at the same time. So not just the way we think about how to understand the concept of vectors and inner product, but also I want you to understand the style of my thinking here, because I like open questions. I like to see how you develop your idea with open questions. Okay. So if you have any unclear point, you have to ask me as soon as possible. More you talk to me or more we discuss, you can get better idea what I'm intending about the class and also the exam. All right, so I hope that I had any time for the matrix part, but I don't have. So we'll continue on section 2.2 next time about the matrix. See you next week.